This is a review of naming ionic compounds. The basic naming conventions are to just name the anion and the cation. So the cation in this case is sodium, and there's 3 of them. And so our name would be sodium and phosphide. We add an IDE ending to the end of our anion. So we keep the cation name. Cations have positive charges, and we add an IDE ending. So in our second example, we name it aluminum oxide. And you don't have to write out all the ions. It's just this is necessary for going backwards. And so one of the pieces that we have for naming is to make sure you've listed out all the ions. The other piece that happens here is that by listing out all the ions, you can make sure that the chemical formula will be correct, because the total positive charges, 3 and 3, will be equal to the total negative charges. We have 6 and 6. When you're going backwards from name to formula, you write out the ions like is shown above. And then, because those ions have to be equal, excuse me, then you need to add more anions in this case, and sometimes more cations, in order to have a balanced chemical charge. The chemical formula is the number of pieces of cations and anions you have. So you just list out the number of cations and anions, and then you have the chemical formula. If you have something called transition metal, and transition metals sit in the middle of the periodic table, then there is no +1, +2, skip a few, +3. There's no column charge that you can rely on. And so the convention is to tell you what the charge is. So in the first example's case, the Roman numeral 1 after silver tells you that silver will have a charge of 1+. After that, the method of solving problems is the same. You add enough cations in order to have the same charge of both the positives and the negatives. And then you put it together in a chemical formula where you write out the number of cations, 3, and the number of anions, 1. Notice that in the second example, there are no numbers, so the assumption is that there's 1 of each of them. And then one of the trickier aspects of transition metals is the lack of a known charge. So for aluminum, we knew it was 3. For sodium, we know it's 1. But for nickel, we don't know what it is. It's usually 2 or 3, but honestly, it could be anything. So the way you do it is, why did we put them together as 1 and 1? It was because it balanced the charge. And so we look at how we put these together to balance the charge. And to do that, I need a 2+ on the nickel, so that 1 2+ on nickel is equal to 1 2- on sulfur. So the Roman numeral here is 2. It's 2 for the charge. It's not 2 because there are 2 nickels. So a common mistake is to think that 2 stands for how many there are, and that's not what it's for. The 2 just stands for the charge. Of course, that would happen. All right, so next is this. Going backwards actually now feels easier because we know that we have the charge of both things. Oxygen is in the 16th column, that represents -2. The only difficult thing here is I get students who think that they're now confused. When I add 1, why didn't that balance it out? And it turns out here that you work with both of them. Oh, I forgot to do that apparently. That you really need a second Fe in here to balance the charges. So we'll need not just one Fe, but we'll need two Fe's, and now we have 6 pluses and we have 6 minuses, and that's why there's a 2 there. Okay, going back to the formula to name method, you add all the pieces, and then you try and balance the charge. So we'll need a 4 plus in order for my 4 minuses to be balanced. And the result is lead and oxide, and then the number you want to add is 4 from Roman numeral. So do the best you can with Roman numerals. There's somewhere in your notes a chart of them. If I saw 4 lines, I would consider that a good guess. So there we go. And then finally, if you see 3 capital letters, here we see 1, 2, 3 capital letters. Here there's 1, 2, 3 capital letters. When you see 3 capital letters or an 8, and it doesn't have to be 8 letters, then you know that you have not 2 pieces that you can put together like we did in the previous ones, but you have 3 that you need to put together. In order to do this, you need a polyatomic chart that lists out the names of each thing. And so that polyatomic chart is in your notes, and so you would just go and find that SO4, or you would find the word nitrate, or you would find the CO3. And again, how do you know when you go to the chart? You go to the chart when you have 3 capital letters. All right, so we have, again, a nickel that sits in the middle of the periodic table, and you have a sulfate that came from the polyatomic chart. And in order for this to get put together, again, I'll need to make nickel 2 plus, so I'll name it nickel 2 and sulfate. And the word sulfate is just written on the chart that comes with the polyatomic ions, which is in your notes and in the reference sheet. Nitrate, so nitrate doesn't end in IDE. Now there are polyatomic ions, hydroxide and cyanide, that end in IDE, and so not everyone is there. So hydroxide is often mistaken for hydrogen as a negative, or sometimes as oxygen as a negative, which is confusing. So, but hydroxide is a polyatomic ion of O and H, and cyanide. There's nothing that looks like cyanide on the periodic table of elements, and so in order to when you look for cyanide, you won't find it, and you'll have to go. Now, again, the other thing you can do is, since the online learning is taking place, is you can type in hydroxide into a search engine, and it will pop up with the right ion. So we're going to take this nitrate and the iron 3, and we're going to put them together. And now it's not balanced, so I'll need more nitrates. So you add more nitrates, and that leads to a formula here. Now, the way this is working is the nitrate has to happen 3 times. 1, 2, 3. So this 3 that's right here represents how many I have. 1, 2, 3. And the other 3 that's inside, this 3, is the 3 that's on the outside. That's part of the word nitrate. So the 3 is part of the word nitrate. I haven't pointed out, at this point, students often add the negative charge because the negative charge is part of nitrate. There has never been positives and negatives as part of compounds. So we don't use the positives and negatives in the compound formula, and we don't talk about it in the compound name. It's only when you're talking about the ions that we actually talk about positive and negative charges. And last example, which is very similar. I have 2 carbonates, so what will the lead have to be? The lead will have to be 4 plus, and so I'll go lead and 4, and then the word carbonate came from the polyatomic chart. Okay, so why do we have these specific charges? Why are there some that have pluses and some that are unknown? So it turns out the transition metals are all have a d orbital, which allows them multiple ways to stabilize their ions. But the S and the P block stabilize their ions by using the an energy state that's stable, right? Quote unquote stable. So what happens is magnesium, for example, will lose 2 electrons to become magnesium 2+, and when it does that, it makes a full octet of 2s2 2p6. Sorry, that's full. The word octet comes from 8 because 2 and 6 is 8. And once that happens, the next magnesium will be reactive, and then the next magnesium. It's not that neon can't react. It is that it is more stable than anything else that's around, and so it basically doesn't react anymore. Germanium has the same thing happens, and it looks like I switched to aluminum here. Sorry. You cannot switch to a brand new substance, so this would be germanium. And so germanium 3+ is formed when I lose electrons from both S and from P. When I lose electrons from S and P, then we do that. Now, positives happen when there is 3 or fewer electrons in the outer shell. So when you have 3 or fewer electrons in the outer shell, then that's what happens. So that would be groups 1, 2, and 13. The nonmetals gain electrons. That is, they pull in electrons. They have this higher ionization energy. So they pull in electrons until they reach the place where they have formed a full octet or a noble gas electron configuration. Here's that full octet. So sulfur, which needs 2 electrons to get 6 as its P, adds 2 electrons, and then it gets there. Now, again, it's stable. It could react, but there's other sulfurs within the reaction mixture that will continue to want to react. And so consequently, this stable S2- just stops adding electrons so that other parts can go. Oh, another mistake. And that's a 2, which I did fix here, didn't fix there. So nitrogen will need to gain 3 to get to 6. And then once it gets to 6, it'll have 3 minus charges, and it will be a noble gas. And that's stable electron configurations that is similar to group 18, which is called the noble gas. So as soon as I fill the S's and the P's, I have created something that's a stable octet, and then it stops reacting. The d orbitals, the transition metals, do not follow this pattern. The d orbitals do not always follow this pattern. There are a few early transition metals that have exactly the same conditions and react in exactly the same way by losing 3 or 4 electrons. But it's uncommon for that large group of elements, of metals called transition metals. All right, that's about it. There's more coming out on the slideshow that I'll share. Just really quick, all these ions click together in an infinite pattern, which we call a crystal lattice of pluses and minuses. Note the pluses have lost electrons, so they're smaller, like the purple, and the anions have gained electrons, so they're larger, like the green circles. And then we call the thing that holds them together electrostatic forces. And then these are the common properties that are shared about ionic compounds. And so it's just full disclosure of information. All right, well, thank you. And I hope this helps.